Hello, today we're going to solve a nice integral involving the floor function and the denominator there. So let's see how we can deal with this. So one idea would be to replace the floor function with a sum of whole numbers, since floor functions always lead to a whole number. So maybe let's see some quick examples of what the floor function actually is. It rounds down to the lowest number. So for example, if you had the floor of pi, that would be equal to 3, or the floor of 2.5, that would be equal to 2, and so on and so forth. So maybe what we could do is just replace this whole function inside our floor function with a variable, something like u, and we can just do a substitution. So we get started by, first of all, bringing the 1 over to the other side and then multiplying by minus 1. So log base b of 1 minus x is going to be equal to 1 minus u. And then we can just exponentiate with the base of b, which will give us 1 minus x is equal to b to the power of 1 minus u. And this means that x is equal to 1 minus b to the power of 1 minus u. And now to find dx, we're going to have to look at this exponential function with the base b. We're going to get dx is equal to log of b times b to the power of 1 minus u. And notice that the minus sign cancels out with the minus sign that comes from the 1 minus u, which apply the chain rule there, which gives us another minus sign. So we're going to have positive log of b times b to the power of 1 minus u du. And then the last thing to look at is our bounds. So what happens when x is equal to 0? What happens to u? So let's just look at this function over here. If we plug x equal to 0 there, we get log base b of 1, which is also equal to 0, so u is equal to 1. And then secondly, when x tends to 1, which is the limit, because at that point we're going to get log base b of 0, which is minus infinity. And 1 minus minus infinity is going to get us positive infinity. So in the end, we've got the integral from 1 to infinity of log base e in this case, so that's the natural logarithm, times b to the power of 1 minus u divided by the floor of u du. And we're going to first clean up this integral so that we can just easily work with what's actually complicated here. So we're going to bring this log of b times b out front in the integral, and then we still have the integral from 1 to infinity of b to the power of minus u divided by the floor of u du. So now we can apply a common trick with these floor functions and integrals of floor functions. We can split this interval up into an infinite amount of parts. So what do I mean by that? Let's see, we're going to have this log of b times b out front, and then for the rest of the integral we're going to split that up. So let's see if I were to split this up into a part from 1 to 2 of our integral of b to the power of minus u divided by the floor of u du, and then secondly the integral from 2 to 3 of b to the power of minus u divided by the floor of u du, and then plus dot 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 all the way up to infinity, right? Now what's interesting here is, for example in this case, if u ranges from 1 to 2, anywhere on that interval except for 2 itself, we're just going to get the floor of u is equal to 1. I hope that's clear, because in that entire interval, we're just going to round down. So 1.5 is just still 1, and except for at 2, everywhere that's the case. But 2 is just one point in an integral, which doesn't really affect it. So we can actually just say that this is an integral where this floor of u is equal to 1. And in this case, we can do the same, and we can just say that it's equal to 2, and so on and so forth. More generally, we're going to be able to write the integral from n up to n plus 1 of b to the power of minus u divided by n du. So I hope that's clear as well for any part of the interval from 1 to infinity. Now, of course, this isn't a very clean way to write this, so we're going to replace this whole thing by a sum. So we're going to get log b times b, still in front, times the sum from 1 up to infinity of the integral from n up to n plus 1 of b to the power of minus u divided by n du. Okay, nice. So now it looks like we've got an even more complicated statement with an infinite sum of an integral, but actually it gets really quite simple right now. So let's continue, and first of all, we're going to notice that this over n right now is not really dependent on the integral at all. It's only dependent on the sum ranging from 1 to infinity. So we're going to get log b of times b times the sum from n equals 1 up to infinity of 1 over n times the integral from n to n plus 1 of b to the power of minus u du. Now this integral over here isn't really hard to solve at all, and we can easily see it's just another basic exponential integral, which is most of the time quite classic if you take any calculus classes at all. So log of b times b times the sum from n equals 1 up to infinity of 1 over n times, and then we're going to get minus b to the power of minus u divided by log of b evaluated from n up to n plus 1. So a couple of things that are important to notice here is we've got this minus sign because we had the chain rule or inverse chain rule for b to the power of minus u, and also of course we divide by log of b. That's just basic integrals and the derivative rules. So next up we can do a couple of nice things. First of all, we can scratch this log of b and this 1 over log of b, and we get a much simpler statement already. Then secondly, we're gonna have this minus sign, which we're gonna put in front, and now we just have to evaluate our statement. So we're going to get minus b times the sum from n equals 1 up to infinity of 1 over n, and then b to the power of minus 1 minus n minus 1 minus b to the power of minus n. Okay, first of all, we're going to take this b and we're going to use it to erase this minus first power, and we're going to multiply it here as well. So we're going to get b times b to the power of minus n. And now we can just factor out a 1 minus b from this sum, which is going to give us, in the end, if we use this minus sign as well, we're going to get b minus 1 times the sum from n equals 1 up to infinity of 1 over n times b to the power of minus n. Now this we can rewrite a little bit just to make it a little bit cleaner. So we're going to get b minus 1 times the sum from n equals 1 up to infinity of 1 over n times b to the power of n. Okay, this sum is actually fairly simple. We're going to use some Taylor series. So if you're not familiar with those, definitely familiarize yourself maybe with some of my other videos about these sums, very similar ones as well. Let's just start off by maybe looking at the most basic Taylor series for 1 over 1 minus x, which is equal to the sum from n equals 0 up to infinity of x to the power of n. Now we can use that and we can integrate both sides, or actually just take the antiderivative, that's more accurate. So we can see that that is going to be equal to the negative log of 1 minus x. So again, kind of the inverse chain rule there. And then secondly, if we term by term take the antiderivative of that sum, we're just going to get a basic sum from n equals 0 up to infinity over x to the power of n plus 1 divided by n plus 1. Okay, and now we're going to change the range of the sum slightly. And we're going to let it go from n equals 1, and of course then we have to get rid of these plus 1s over here. So still the same sum. And now you can maybe see that it's actually really similar to what we need. So let's say we were to evaluate this at x equals 1 over b, right? What would that give us? Well, we would get minus the log of 1 minus 1 over b is equal to the sum from n equals 1 up to infinity of 1 over b to the power of n divided by n. And of course we can rewrite this as the sum from n equals 1 up to infinity of 1 over n times b to the power of n. Okay, amazing. So we've got an expression for our last sum here. So we're going to get b minus 1 and then this answer over here, which is the negative log 1 minus 1 over b. And maybe one more cleaner way to write it is going to be 1 minus b times the log of b minus 1 divided by b and this is our final answer. And maybe it's nice to see what this looks like visually. This integral actually looks quite nice visually. So we've got a nice closed form for any integral involving this floor function, and of course for any base of b, although b of course does have to be bigger than 1. So for example, if you were to want the integral from 0 to 1 of 1 over the floor function of 1 minus log of base 2 of 1 minus x dx, well, that would be equal to, let's see, minus 1 times the log of a half, or in other words, log of 2. So quite a nice answer, but thank you so much for watching. I hope you learned something about floor functions, especially about integrating them, how we can use these sums to actually make it into a much simpler problem, just calculating a series eventually. And I think these are really nice videos because you're both learning about integrating and learning about this other interpretation of a sum, of an integral, which is especially useful when you're using floor functions. So till next time, if you've got any tips on how I could have done this differently, if there was a simpler way, definitely let me know. Till next time, thank you so much for watching.